In the general linear systems problem, my claim is we are going to be working on a forward or a backward problem. Backward problem, right? Because I'm given a matrix and an output. In other words, I'm giving a function and an output, right? Backward problems, I'm giving a function and an output. Okay. Claim, this example that we just went through represents a very, very nice analogy for all possible options that we're going to have in the general linear systems problem. How many different options do we have for types of solutions in general linear systems? 3. What are they?
Non-unique, non-unique.
Unique solution, okay. Non-unique solution, no solution. So let's write that up. Let's write that up over here. And I'm not going to ask you to worry about this at the moment. Remember, the whole way I'm trying to have you think about this is we are constructing the foundation, the frame of a house. And as we build matrices, as we build theory, as we go back and look at our set theory, the whole idea is to fill in the gaps between this foundation. But I want this foundation really, really strong so that as you build that nuance, you actually are forward looking. This is, mathematicians often call this the difference between seeing the forest from the trees. Every lesson that we're going to do, we're going to get a microscope out and we're going to look at an individual tree in the forest, right? But I want you to have the option to get into a helicopter, go to 10,000 feet, and see the entire forest. And that's what we're doing right now. We're actually looking down at all of linear algebra, introductory linear algebra, and be like, oh, look at that plot of land over there. That's where the hobbits live. Oh, look over there. That's where the elves are. Oh, that's where the orcs are over there. Right? The orc is called calculus, right? No, I'm just kidding. I'm just kidding. Okay, so in general linear systems problem, I'm going to just go GLSP. We will see we have how many options? 3 options for solution type. So don't trust anything I'm saying. I want you to just blatantly disagree and not believe me. Because my job this quarter is to get you to a place where you can conclude this for yourself, right? What was option 1? Yeah, my claim is it's going to be a unique solution. So let me ask you this. What is under every single problem that we're going to work with? What function is under every problem that we're going to work with? Matrix vector multiplication. Okay. When does a backward problem have a solution? What must be true about the output that I give you in order for that thing to have a solution? Yeah, so given output, damn, is that linear algebra? No, it's set theory, right? If I claim that I'm giving you a backward problem, in other words, I'm giving you something in your codomain, and I expect something in your domain to map to it, when does that happen? When it's in the range. Given B element of, oh, sorry about that. We call it the range of F. We're going to figure out what that means. And A must be what we call full rank. And really, if I want to be too legit to quit, I should say it's full column rank. Do we know what full column rank is? Not yet. Not yet. We're going to get there. That's called lesson 6. In lesson 6, we will set the foundation for what full column rank is. So what's the whole idea? General linear systems problem, what are the options we have? Unique, non-unique, no solution. When is it guaranteed to have a unique solution? First of all, the output that I give you has to be in the range, and then the matrix that we're analyzing has to be semi-special. Full rank. Full rank means rectangular, but the same properties of non-singular hold. And we'll get there, don't worry. Right? So you could imagine that full rank is the generalization of non-singular. Non-singular is the prayer. Full rank is the nice, like, I'll settle. Right?
Is full rank similar to one-to-one?
Yes, actually. In fact, yeah. 12 lessons ahead of your teacher. Yeah. 1, 2, 1. Okay? Okay, could you guess what option 2 is? Non-unique solution. Okay, when is there a solution? When does any backward problem have a solution? I almost want to go back here because you seem so engaged here. When does any backward problem have a solution? What must be true about the underlying function? The given output has to be in the range. It has to be hit by the function, right? So we're going to be given B element of the range of f. And, okay, could you guess? We have a unique if the thing is called full rank. When would it be non-unique? I need a pipe and a beard. Yeah. And A, what we call rank deficient. AKA, A is not full rank. And as my friend Joe said, what does that mean? Not 1 to 1. Okay? And remember, just the thing I'm going to encourage you to do is, every time we're learning math, I'm encouraging you to set placeholders. Just like a rock climber, right? What a rock climber does every time they advance to the next height is they find a place to hold so that they can leverage that muscular motion to get up to the next one, right? So these are all placeholders that we're going to come back. We're kind of mapping our route. Okay, what's the third option? For the GLSP. What did we say the third option was for that non-singular or non-linear or what we call quadratic function? No solution at all. Okay. When does a function, a backward problem, so I give you an output and I'm looking for an input, when does that have no solution? When the given output is not in the range of the function. So given a B element of the codomain of f, what was the codomain of f again? For general linear systems problem? R mango. Because of the size of the output, right? But B not an element of the range. In this case, the GLSP has, can you guess what I'm about to write? No solution, but we can think about, well, what did we do in that case? When there was no solution over there, what was a hint that we gave? Minimize the distance between the possible solutions and the given output. But we can think about minimizing the distance between the range of f and the given b. Do you know what we call that? This is called problem 4. And I also think, actually what I forget, I think I might have called this problem 6 as well. One of them is called the full rank least squares problem. And the other one, can you guess what the other one's called? The rank deficient least squares problem. Could you guess what the full rank least squares problem is? What's true about the matrix A? It's full rank. Could you guess what it means when you have the rank deficient least squares problem? Not full rank. And we're going to get there. I don't want to worry about that today. We're going to fill this in later. The reason that I wanted to do this today is I just claimed that I wanted you to waste probably 5 to 10 hours on your life on set theory, right? I should ask Irene. Irene is a very, very deep studier. How long did it take you in the last few days?
About like 5 hours, but even then
There's a lot going on there, right? Yeah, so I'm making you suffer for a long time, and you might think to yourself, like, what the hell is this guy doing? This isn't a set theory class. This is a linear algebra class. Okay, what's the main, literally in this class we're going to solve 6 problems. Problem 0, problem 1, problem 2a, problem 2b, problem 3, problem 4, and that's it. Okay. This gets us through 4 of those. I didn't even talk about this one yet. This gets us through problem 0, problem 1, 2a, 2b. What's the claim about the difference between problems 1, 2a, and 2b? Where's all the different, and number 3 actually, the least squares problem. Where's all the difference lie? Check out the conditions. Okay, screw this for a second. Screw this. What are we doing? We're doing an overview of the class, right? How many problems do we have in this class? 6. Okay, problem 0? Real world problems. Solve real world problems. Create matrices and vectors from stuff that you can measure. Problem 1. Forward problem. I give you a matrix, I give you an vector, an input to a matrix vector multiplication function. What do you produce? Single output. That's a forward problem. Start with the domain, go into the range. Yep.
Is the vector also experimental?
Let's talk about that. We'll get there. Okay. Okay, so that's called a forward problem. I give you an input to a function, I give you a function, aka a matrix. You take the function, take the input, take the function, produce an output. Problem 2a. Non-singular systems problem. Very, very special function. What do? Instead of me giving you the function and the input, I give you the function and then what do? Find the pre-image. Guaranteed, if it's a non-singular system, it's both onto and one-to-one. In other words, it will always have a solution, and that solution is unique. That's one of the most sexy things about non-singular linear systems problems. Every output always has a pre-image, and it always has exactly 1. Okay, what do we do once we have a non-singular linear systems problem? What's the claim once we've got our head around that option? Generalize. In a general linear systems problem, what's the claim? Instead of looking at a specific type of matrix, what do we do instead? Generalize. So no longer does it have to be non-singular, no longer does it have to be square. In that case, in the general linear systems case, what did we claim about our different options for possible types of solutions? There can be a unique solution. When does unique solution happen? When the output is definitely hit by the function and when the function is 1-to-1. Yeah, and we say that in matrix stuff. That means that the matrix is full rank. What does that mean? Who knows? Right? But we'll get there. When do we say non-unique solution? Output is hit by the function, aka it's in the range, but the function is not 1-to-1, aka the matrix is rank deficient. What does that mean? Please rain down upon me knowledge about rank deficient matrices. See what happens, right? Okay. What's the third option? No solution. What does that mean? Output vector that we were given is not hit by the function, in which case we're going to minimize the difference between the range and that given codomain element. That will be called in this class, for introduction, full rank least squares. And we'll get there. I don't want you to worry about that yet because we don't have norm notation yet, but we will get there. Yeah.